Hello and welcome everyone to today's webinar. We've got two talks today for our emerging technologies and novel design in assistive and rehabilitation technologies meeting. Please ensure that your microphone and webcam remains turned off all the way through the talk, and if you have any questions or difficulty registering, please direct that to the host IPEM in the chat facility, and I'll try to assist. If you have any questions regarding the talks, please direct them to me, IPEM the host, and I will direct them to the speakers at the end. This is a recorded webinar and it will be available after the meeting on YouTube later in the week, and that will be available on our website. And thank you, and I'll now hand over to our speakers. Thank you.
Hi, my name's Mairead and I'm from the Clinical Engineering Innovation team based in Cambridge. So today I'm going to talk about conformance routes with the EMDR for a range of medical devices. So the contents of my presentation today. So I'm going to start with a bit of background and context to the team that I work within. That will probably help when it comes to explaining some examples. I'm also going to then talk about what range of medical devices that our team is involved with. I'm then going to talk about different conformance route issues that we've experienced with these, a bit about the difference between different routes, and then I'm also going to touch on human factors of medical device design. So who is Clinical Engineering Innovation? So we are a team of 7 engineers and 1 admin assistant. We have a background of different engineering specialities within the team. So we have 4 clinical scientists, 3 of which went through the STP training scheme, and then another one who went through the Route B qualification. We then have 1 clinical engineer who has a background in clinical engineering technical services, and then we have 2 engineers who have come from sort of external industry experience. And I think having this range of backgrounds within our team is very useful and very important to us being successful in the work that we do. So we're based within Addenbrooke's Hospital. So we sit within the main building and we share a corridor with medical physics. And we sit within clinical engineering. So our team was initially started from engineers working within the technical services who started to do some design and development work sort of ad hoc, and over the years they managed to build that up and to demonstrate its value to the trust. And it's taken maybe 5 or 6 years for the team to develop the sort of dedicated full-time roles that we now have, but I feel like our purpose and value within the trust is continually being demonstrated, so hopefully our team will keep growing. So what type of work do we be involved with? Our work falls into 3 main categories, so I'm just going to skim through each one quickly. So the first one is medtech consultancy, and this is where we offer a route for external companies to access information, clinicians within the CUH Trust. So most of this work involves setting up requests from external engineering companies who would like to speak with, engage with clinicians working in a particular area. And this usually is around them developing their own products and then wanting that clinical feedback. This can also expand to access to clinical areas, running more active workshops with clinicians. And we have quite a well-established process for facilitating this work, which means that the R&D legal team are involved to make sure all areas of IP confidentiality are covered, and also from a costings point of view, it ensures that all departments or parties involved within the trust are then reimbursed accordingly for being involved in this type of work. So it provides an income to the trust and to our own team. The second type of work is manufacture and modification of equipment within the trust. So we do have a workshop within the trust which is currently going through a bit of a revamp, and from it we can then offer modification and manufacture of equipment. These can range from quite small, short turnaround jobs to quite larger ones, and they involve both medical devices and more non-medical but possibly lab equipment, hospital equipment that needs modification. And thirdly, probably our largest portion of work that we're involved with is engineering design. So this is where we work firsthand with clinicians, mostly within CUH, to do a design and manufacture project. We do also work with clinicians outside of our own trust, but most of our projects are internal. So what range of medical devices do we work with? So I'm sure some of you have sort of come across these within your own work. They're quite common classifications, but most of our products fall into the in-house classification. So just to kind of put a number on it, it would be around, if there was less than 5 devices that we were manufacturing to be used within our own trust, we would use this exemption. There's also no commercial intent with the device. So that means that we have assessed the device and decided that it is only to be used by clinicians within Addenbrooke's, and in the long term we see no commercial potential to commercialize the product. So an example of this is an adapter that was manufactured for insulin pumps within the trust. So that was to help patients who didn't quite have the muscle activation to administer insulin themselves. So we then manufactured an adapter to enable them to do this. And there's currently 2 of those devices, and they're available in the medical device, medical device library, and clinicians can request those devices as and when there's a patient that requires one. The second one is a custom device. So this is where a specific device is designed and manufactured for a specific patient in mind. And an example of this is a prosthetic end terminal device that was manufactured and designed for a specific patient from the prosthetics department. And the third type is a CE mark device. So this is where we do see commercial intent for a device, and we would in the long term want to commercialize it. This also applies to if we wish to supply a device to an external trust, it then has to also go through this process. An example of this is the CAN probe device that we were involved with. So the device is used for taking biopsies from the prostate, and it's currently going through a clinical evaluation within our own trust and neighbouring trusts, and that will then form part of the technical file for the CE submission of that. So we do be involved with other types of devices within the trust. So as I mentioned, we are involved with manufacturing and modification of equipment, and this may not necessarily be a medical device equipment, it may be a lab equipment, some sort of calibration equipment used within the hospital. And we are so happy to take these jobs on, even though they aren't classified as medical devices. We then also have, quite similar to this, a grey area of development, which is where we have requests for a device which has a query mark over whether or not it is a medical device. And as a team, we then assess these and determine their classification. And some of these do fall out of not being medical devices, and for the sake of this presentation, I've called them hospital devices. And sometimes this can be difficult to determine, and you do have to go through the fine details of medical device classification to get an answer. And as an example, project that fell into this category. It was a piece of physio equipment. So the device there in the image, it was a storage unit for physio equipment that would be used for patients that are in isolation. But the physio department also wanted them to be able to use the storage box as a step to do some exercises on, and also some tie down points for exercise bands. So we then had a sort of internal discussion on whether or not that was classified as a medical device. So I'm going to talk through some issues that we've experienced within our own team regarding the classification and then the conformance route for projects. So I spoke about this already, but we were involved with the design and manufacture of an end terminal for a prosthetic limb. And this project in the first round was very much a custom device. So it was designed and manufactured specifically for one patient. But after that one patient had the device for about 6 months, and we were getting very good feedback from him and how it was functioning and how it was helping him with his own functionality. The prosthetics department then had a second patient who they identified could benefit also from this device. So we then had to establish how we would hand over this second device to the second patient. The device had to undergo no design changes to make it suitable for the second patient. It was going to be an identical part to what was initially prescribed. So it therefore did not fall under the custom device option. So we assessed the feasibility of putting a CE mark on the device. And here we ran into some issues regarding harmonized standards. So the MDR has a list of harmonized standards which would be considered a vertical device standard, so they're specific to a certain type of device. And by complying with the MDR, you then also have to comply with if there is a relevant harmonized standard to your device. And in this instance, there are some harmonized standards for lower limb prosthetics. So I've just showed an image of one here. So therefore, if we wish to CE mark our device, we would then also have to comply with these harmonized standards. And to do that, there are test centers available which will test your product under very controlled conditions, but this does come with a cost. So we reached out to these test centers and got some quotes for what testing would be required for our device and the cost of this. And we then assessed the cost, and we decided that the cost benefit of CE marking the device, it wasn't in the favor of putting a CE mark on it. So we then decided to go under the in-house option for the device. And to do that, we then took guidance from these harmonized standards, and we were able to do some in-house testing. So we linked up with the Gate Lab, and from it we were then able to do some FEA analysis on our part. And this was taken from guidance from data from the Gate Lab, but also around loading conditions, mechanical loading conditions from the standards as well. And we were able to generate a report from this. And as a team, we were then happy that that satisfied us for in-house use. So we therefore converted the technical file from a custom device to an in-house device. I'll also make a note that this is quite an exceptional circumstance, and this doesn't happen too often with our devices, but it's still quite an interesting case. So another problem that we're discovering is the up classification with the MDR. So the classification of the devices has changed within the MDR. And unfortunately, one of our devices, which we had CE marked under the MDD, has now been up classified by the MDR. So this then now means that we're unable to supply this to external trusts, which is something that we had intended to do for the product. We are now looking at whether or not it is economically sensible for us to reissue the CE mark under the MDR. As to do that, that piece of work will cost our team quite a lot. We then have to look at the cost benefit of doing that and then being able to supply it to other trusts, whether or not it's worthwhile. And I'll just make a note here, if anyone's of interest, that the MDR is possibly going to be delayed by 1 year. So I've included some links to that. Another conformance route that we have issues with is if we wish to supply something outside of our own trust. So we had a request from the university that was running a research trial in partnership with the trust, and they wanted a device manufactured for this. It was very low volumes. There was no commercial potential in the product, but still for us to be able to supply it to the university for their trial, we had to put a CE marking on the product. So this just shows what the project was. It was a cap for an insulin pump. So a very simple design, and we 3D printed 200 units, and that was then what was CE marked for use in the trial. So another conformance issue is the medical device versus a non-medical device, and when this kind of arises its head. So I mentioned before that a piece of physio equipment kind of fell into this grey area, and we had queries within our team whether or not it was a medical device, and the physio themselves also were kind of undecided about this, but it's an ongoing discussion. So the box is to facilitate self-guided physio for immune-compromised patients. So that's patients that are in an isolated room for a period of time, up to several weeks. And the physio department would like them to be trying to maintain some strength and fitness during this period. So we then looked at what the different options for this were. So we were able to provide the physio department with an off-the-shelf storage box, which was simply buying a strong, sturdy box and providing it with them. So there'd be no functionality involved regarding the patient. It would be simply a storage box, therefore not a medical device, which is that image there. We then also could go down the custom route, where we would design and manufacture them a custom box for the patients. And this would fall into two categories. So it could be a medical device, and it also could not be a medical device. So we then costed up what the documentation and testing would be involved between those two different classifications. And we were then able to put a cost on that. And even though the cost included in that table, it would not be billed for by anybody. It was just so as a team we could appreciate in money terms what time it would take between the two options. And we're now working with the physio department to assess the functionality of the box and to decide which option will go down. This project is quite similar to the previous one. We were approached to manufacture a trolley for an organ perfusion system. So you can see in the image, this is a liver perfusion system that's used within Addenbrooke's, but the product has been designed so it can only be used at floor level, and it can be transported, but again, this is only at floor level. And clinicians are having issues when using it in theatres that they have to bend over. So it's inconvenient, but also from an infection control side, it is not the best either. So we were then approached to see if as a team we could design and manufacture a trolley for this system. And with this case, is it a medical device or not a medical device question came up. And looking through the regulations, we decided that if the function, so if the design and the functionality that the design provides can be restricted, then we can ensure that it's not a medical device. So in this project, we decided that we didn't want it to be a medical device, and we then therefore are designing something around that decision. So the trolley cannot add any functionality to the part already. It has to be, I'm going to call it a dumb part, where it doesn't add any additional functionality that the part already does not have. Just to bear in mind that by it not being a medical device, it is exempt from the MDR, but there is device-specific standards still that it must meet. So there are medical trolley standards that it still must comply with. So even if your product is not a medical device, there may be standards still applicable to it. Another conformance issue which rises ahead sometimes is the legal manufacturer. So with all handover documentation, a legal manufacturer must be stated for a device. And with some of our projects, the team involved with the project can be quite large, and there can be several bodies taking on different roles. So just this screenshot is from the CAMPRO project. So that was the prostate biopsy, which is currently going through a clinical investigation. And that project has quite a large project team. And in that, it then has to be determined who is the legal manufacturer. And in certain instances, bodies cannot be jumping at the chance to be that person, because you do take on quite a lot of responsibility for the product. So at times it cannot be an easy decision to be made. And with a similar project, we are having a similar project which we are partnering with an external company with. We are having an ongoing discussion over who is the legal manufacturer, because in that instance the trust isn't so keen for taking that responsibility on. So this can sometimes be an issue. Okay, so I've sort of highlighted the different conformance routes that products can go down, and then some issues that we've had with projects within our team. So I will now talk quite briefly about conformance route differences for projects that we take on. So regarding the three classifications of medical devices, so the in-house, the custom, and CE marking, if I'm quite honest, there's very little difference between how we deal with those three categories. In terms of our design process, each device, irrelevant if it was an in-house or a CE marking, would still go through the same process. And the fundamentals of that are still the same. Each of those does have to comply with the general safety and performance requirements. And because that list is so expansive, there's very little documentation or activities that you're exempted from. If it was an in-house or a CE marking, they still have to be completed. Regarding what the difference would be between an in-house and a CE marking, you may not have to involve a notified body for an in-house device, whereas if you want to CE mark it, you then have to have your technical file reviewed by a notified body. But in terms of that body of work, it would still be the same. It just would difference between who ultimately would be assessing it and whether or not it would be assessed. Between our in-house and CE marking, some documentation may be reduced in detail and depth, but there would not be any gaps in the technical file regarding documentation. Some may just be not as in-depth as others. Regarding the manufacturing projects that we're involved with, they are very much a separate process. They would not go through our design process, but they themselves do have a defined process and there is a defined set of documentation that is required for those as well. So that was quite a summary. I think the ideal would be that I could have provided how our technical file differs between the different routes, but all documentation is still ticked off for each route. So unfortunately, I could not provide one of those. Okay, so I'm now going to talk a little bit on human factors and how that comes to play in our work. So what is human factors? So it's quite simply where you consider who your user is, where your device is going to be used, and how that user is going to interface with your device. And you consider all of those aspects in your design, and you in some way incorporate that information into what you design. And then that can then improve the safety and the effectiveness of the design that you come out with. So why should human factors be considered? From the legal stance, the MDR, General Safety and Performance Requirements, has at least 4 statements where it refers to human factors. So I've just very much copied and pasted 4 of these here. And I've just highlighted some of the points that it raises. So it talks about the environment, talks about the users, the intended users, the use environment, the ergonomic features, intended purposes, environmental conditions. So it's very much covered. And even as an in-house device, those requirements have to be complied with. So even for an in-house use, you still have to comply with human factor requirements. There is also a harmonized standard, which is the 62366, and that is usability engineering to medical devices. So again, similar to the prosthetics device, because the standard is harmonized with the MDR, if you can demonstrate compliance with that standard, you then demonstrate compliance with the human factors aspects of the MDR. Okay, so if you want to do some human factors work within your own design and development projects, how would you do that? So there are good resources available that can help you through that process. So I've just listed some here. So there is the standard, which I previously mentioned. The MHRA has a really good document on it, which I'm going to talk about further in the next slides. I can't pull that out, but the University of Cambridge, so that middle image, has done a lot of really good work on human factors in medical device design, and especially around the safety issues that they incorporate. So I very much recommend having a look at the University of Cambridge Engineering Better Care group and the work that they've done around it. And they have some very good examples where better human factor considerations would very much improve design of devices. And there's also 2 groups which are useful for engaging with. One of them is called the Clinical Human Factors Group. So it's a charity that started from, I believe, a clinician whose wife died as a result of bad human factor design of a piece of medical equipment. And they run sort of workshops and events, kind of education days for designers, clinicians to attend, and they're trying to sort of promote human factors in medical device design and the benefits of it. And the days tend to be either free or very cheap for NHS staff, so I'd recommend having a look at them. And then also NASA have really good guidelines around anthropometric dimensions. So if you're designing parts and you need sort of guidelines on what dimensions that part should be related to the anatomy. NASA have provided really quite in-depth resources for that, and it's actually really interesting to see some things that they've come up with, so I'd recommend having a look at that. Okay, so how to incorporate human factors into your work. So the document that the MHRA has published is Human Factors in Usability Engineering, Guidance for Medical Devices. And this is a free resource, while if you try to access the standard, the 62366, quite likely that you'll have to pay for it, unless you can find a PDF somewhere online. But the MHRA is free, and it's quite a useful document and quite a user-friendly document to use. So this is the human factors process, and I've just copied this table from the document. So I'll just kind of walk you through it quite quickly. So each box refers to either a document or an activity that you would have to do in human factors. So you start by stating who your user is. And that's very simple things. What age are the users? What's the demographic? You know, are they going to have any visual issues? If it's a, you know, kind of thinking of more rehab stuff, if it's an ability thing, do they have certain dexterity or function that might impact design? So you just list out who your user is. You then you also then look at a use specification. So that's where you state what the product is, where is it going to be used. You then start to look at what other devices are on the market. And if you have, in some way, if you can pick out if there's been any use error with those previously. So just, again, thinking of rehab examples, if you were designing a new switch for somebody, if they've previously used an off-the-shelf switch, you could get feedback on their experience with that, what was good about it, what was bad about it, and then you can then incorporate that into your own design. You also can look at post-market surveillance on products. You can look up it on the MHRA if there's been any incidents with products. That's all really valuable information to incorporate into your own design. So you then have to risk assess what your use area is. So that's where you would sort of think into if it was a wheelchair switch, you would sort of risk assess if it's used inappropriately, what is then the risk to the user. So with the switch, if somebody can turn the speed up too quickly, what is that then going to cause? If they turn it down too low, is that going to be problematic? And you would then risk assess that. You can then start to prioritize what the tasks are involved with your device. So with the switch, you know, you could say, you can list out the functionalities of the switch. You know, it's going to turn up the speed, it will turn down the speed. It might control the lift of the chair, the incline of the chair. And then you can start to list those out. From your risk assessment, you'll know what's quite a risky task. So thinking back to the speed, and then you can then focus in on that as a specific task. And you can then do an assessment on your user, maybe using a prototype or maybe having a volunteer using it before your user themselves actually comes into contact with it. And you then do some testing, so looking at formative testing, and you will then, out of that formative testing, you can then iterate your design. And this then starts to go into a continuous loop for users. Oh, sorry, computer's doing something. So formative testing is sort of an iterative loop where you will test a aspect of your design, and you then might iterate it based on what your user feedback was. And then at some point, you'll say, okay, I've done enough formative design, I'm ready to test my final product. And that is what your summative testing will then be. And then once you've done that, and you're happy that there's no user errors involved with your device, you can then write a nice summary report, and that's what you would then submit for your device launch. So also within this document, each of those steps is, there's quite in-depth background to it, much better than what I've just tried to state myself. So I would recommend having a read through the document, and it talks you through each stage quite clearly. So if we were to look at this process for custom and in-house use, I would recommend having several rounds, most likely of formative testing. Summative testing is more, if I'm honest, the two, what's involved in both rounds is quite similar, but summative testing would be more associated with if you were doing a clinical investigation to then see market advice, but having several rounds of formative testing and then a report would be sufficient for a custom and in-house use, but that's only my recommendation. I wouldn't fully take my word on it. And then just a note that within custom and in-house use, human factors is really valuable and much easier to do than if you were looking at a CE mark device. The reason for that is, especially with custom devices, you have one user, so it's very easy to define what your user requirements are and what your user need is, because you're designing for a particular user. You're not designing for a range of clinicians who have a range of skills and backgrounds. And also you can control your users, so you know that the device is not going to be used by other people. So I think with the in-house and the custom routes, human factors as an activity fits quite well, because you have that control over who your users will be. This is an example of some usability testing that our team done. So this was for the CamProbe device, so for the prostate biopsy. And this was just a 3D printed prototype that were glued together. And then they've used it on a prostate ultrasound phantom. So this was testing some early stage prototypes. And this was the results were a range of clinicians that tested the prototype. And within the testing, there was certain tasks that were highlighted as being the high risk tasks, and it was them that were then looked at particularly in the usability testing, as sometimes it can be difficult to assess a whole process. It's quite useful to pick out what those high risk tasks are. And finally, this is a slide from when I went to one of the days run by the charity, I forgot the name of them, sorry, I'll flip back. The Clinical Human Factors Group. And it was from a team that look at human factors and safety around medical devices. And they just had a quote from a procurement professional. And in it was said that we don't want to duplicate the MHRA work. We assume that they are safe, as in medical equipment are safe because they're already on the market. And it's just to sort of make the awareness that human factors is not always considered in design. It has been written into the MDR, but it wasn't as identified in the MDD. So devices that you're already using may have had little to no human factors analysis done on them. So you cannot assume that from a human factors point of view that they are safe and suitable for usage. And I just think as engineers working with equipment, it's good to bear that in mind, and that equipment may not be fit for use from a human factors point of view. Yeah, so that's kind of a finished note. So that's me. So thank you. My colleague Charles is now going to talk after me. And I think once Charles finishes, there will then be time for questions to the two of us. So I'll pass over to Charles.
And the mechanical engineering technician of clinical engineering innovation, and I'm going to give you a very quick run through about the manufacturing methodologies for prototype and production that goes on at Addenbrooke's Hospital. I'm going to go through my own background, give you 5 examples that are already come. Mairead has actually already mentioned some of those, and then I'm going to give another detailed process of 2 more at the end. My own background, I had an art scholarship back at school. I then went to Lancaster University. I got a 2-1 in mechatronic engineering and competed in Formula Student. I then still couldn't decide what to do for a career. Went on to do PGCE secondary design and technology. Decided that that was just a little bit of a waste for me. My skills were being wasted, but I did learn a lot of things. Since then, I've bought my own little machine shop, started making things, really started having a go at doing lots of different things, not getting stuck in one way, and lots of different materials. And finally, I'm also a member of Toastmasters International. What I'm hoping is that while I'm speaking, I'm not going to err, I'm not going to sew, and this is going to be a good, quick presentation. So CAM probe. The original prototype was made of stainless steel. It was reusable. That meant that it could be sent down to sterile services to be cleaned. The only problem with that was that it was stainless steel, meaning that it was very expensive to manufacture and there were very few produced. Instead, a single-use version was created. This used injection molded plastics instead to replace some of the, what I'm going to call, more expensive parts, which meant that they could be reused or not reused in this case, and therefore, because they could be thrown away, they could be much quicker, and in some cases, a lot more could be manufactured, which is great because this can now be given to lots more hospitals in a mass production. Pain relief. Mairead said it was an insulin pump. By the way, it's actually for pain relief. The original prototypes were because people's hands literally could not press the buttons. When you're in hospital and you're in pain, the first thing that might happen is you've actually injured your hands as well. What people were finding was they didn't have the dexterity to push the button to offer them the morphine or other pain reliefs that could be literally pushed into you and pumped in. People started looking at different designs to give much more leverage, including using a spoon. Quite a big spoon as well, by the way, and went through a few different iterations. The 2 that have been produced that are in the medical image library now have actually been 3D printed. Quite interesting that, because that's a much quicker manufacturing method than making that out of a machine using either a mill or a lathe. Prosthetic limb for the Invictus Games, again, another one that Mairead mentioned. The original prototypes were designed literally to fit on the bottom of the cleat. The cleat is the part that literally cranks the bicycle chain around, and that's attached to the pedal. The original tests actually were produced on CAD for stress analysis, as Mairead had already mentioned. And then a few more iterations were produced to make sure that these were suitable for the user. The user in the Gate Lab included some of the nylon 3D prints, but the final one, to ensure that it worked properly on the user, was machined quite literally from a CNC machine and produced using CNC of aluminium. the dilators from prototype to production. The original dilators look quite uncomfortable, but the use of what they are going to be used for, stainless steel, cold, hard, quite a nasty material. Someone thought that maybe these could be made from a polymer, a plastic such as acrylic or perspex. The in-house versions were originally made from two pieces. One part was the solid rod, and the other part was the handle, which people can hold. Unfortunately, these were bonded together, but had a lot of failure rates and a lot of quality control issues. Eventually, a manufacturer was found who could quite literally CNC machine these. These can be manufactured in much larger quantities and can now be quality controlled in the hospital, which is great because they are now come back polished far better because the manufacturing methods are far better. Again, the insulin pump cap modification, quite an interesting project this. The insulin pump caps that the users already have in the hospital have a clockwise thread. The pump that was used and bought off the shelf had an anti-clockwise thread. The users always liked the needle sets that were used for the clockwise thread, and there were very limited numbers and designs that could be fitted with the anti-clockwise thread. The users really wanted, quite literally, the sets that they were already using, a clockwise thread. As a result, it was a very simple modification. Just take the cap off and then put a new screw thread in. The original ones were literally put on a lathe in the workshop upstairs, drilled out and a new thread fitted. Problems with these, again, the adhesive was failing, and these were very, very hard to manufacture very quickly. Only a few could be produced in tens. A manufacturer was found who could use a carbon resin, and they could now be put on a plate and manufactured in much larger batches, and therefore given to much larger numbers of patients in the research project. Finally, my detailed manufacturing project shows something that comes from much simpler and quite an interesting material, because what you're not going to expect is that we also do a bit of woodwork. Neuroangiography have copper plates every week that need to be quality assurance tested. The problem is that these plates have to be held in place, and then the test is confirmed. If they get a white image on the back, then it's passed. If there's anything on the image, then obviously it's failed. The problem they've had is actually holding the plates. There's nothing that comes with the machine for the quality assurance tests to hold the copper plates. In quality assurance and the neuroangiography, they sent me down, go on a trip down, have a look at what they've got. Quite literally a piece of 2 planks of wood on a piece of plywood. But the problem was that the gap wasn't big enough, or in fact it was too big. What they asked was for literally the same design to be produced, and it was quite a simple project, but there was still a thought process that went behind it. The copper plates weighed quite a lot more than what I'd initially anticipated, being 2 millimeters thick. They were coming on for over 1.5 kilograms. The base that they were going to have to slot in was going to be quite a simple construction, but it couldn't topple over. The idea was that the clinician could quite simply place them in without any obstructions, but the fit needed to be a clearance fit. It couldn't be a location or an interference fit because the clinician didn't want to damage the copper plate. This meant making sure that the gap inside was literally just over 2 millimeters. The plate couldn't rock inside the stand, but it had to be able to literally slide in and stay in place. The easiest way of manufacturing this and making sure that it was that fit of a clearance fit was to put in 2 pieces of paper and a screw and glue construction. And I thought, what about the future? The future of this device, if they change the copper plates at all to a different thickness, I'm going to put in wood glue screws all over. But no, actually, I'm going to take out the wood glue from one side. I'm going to ensure that that other side, I can alter the gap later on. Very simple. Clamp up, glue, let it set, leave my plate in. Plate's not the same, but it's the same thickness. And hey presto, there we go, 1 plate holder for the neuroangiography department. Finally, the detailed manufacture of the other one was requested by the East Anglian Regional Radiation Protection Service. Quite an interesting one, this. It was as simple as lowering the height of a very simple standard that had actually been created in the department quite a long time ago, well before I came. And on first inspection, we often do a first inspection. What I've learned is that you've got to look a little bit harder when you want to do a modification, because yes, it's really easy just to cut a few pieces out, but actually you've got to do a little bit of investigation before you get through to what you're going to do. Remember, measure twice, cut once. The only problem is you also got to investigate twice before you make that cut. 200 millimeters. It looks simple. Cut a bit of aluminium out, you've lowered the height. What I actually found was that on first investigation, there were quite a lot of screws, nuts and bolts in places that were literally holding the whole piece together, not just holding it together, but in quite critical locations. Like a jigsaw puzzle piece, if it didn't fit back together, it wasn't going to go back together properly. What I realized is that I actually had to deconstruct the whole piece, take out material from the centers. What I also wanted to do, as I did with the neuroangiography device, was to ensure that if they ever have a problem in the future or want to change the height again, I want to make it so that it slots back together again. I can add in extensions if I want. What I did, I took the device, deconstructed it down to its simplest form, took it out, made some pins so that the device slotted together. And hey presto, one device that's been lowered in height. And the pins that I decided to make were 8 millimeters. The depth of them was deep enough that the device couldn't topple over and it couldn't be deconstructed again, but that I could put in extensions when I needed. Everything slotted nicely together. But they also said, just in case you want a little bit more information, they've got some extension poles as well. We want 200 millimeters taking off again. Same problem is, got to do a little bit of investigation. By doing the investigation, what did I learn? There were critical features that needed to be retained again. If I didn't include those features back in my design, the whole thing wouldn't slot together again. It's as simple as that. What did I come up with? A design that I could actually change later on. Should they come back to me and say, got a problem, we need a different source, we want to change the height, I can always take it out, and because I've left designs behind, anyone else who looks at it, they'll know what to do next time. And thank you very much. I hope you've enjoyed it.
Thank you very much, Charles. I'm just going to share my screen with you both, and we've just got one question. If I just share that. So we've just got one question. It's just, is the team involved in any project related to COVID-19? Don't know if I can still get access to Mairead. Hello.
Hi, fine.
Sorry. Thanks.
Yeah, no, we are doing work for COVID-19. Myself and Charles are particularly looking at aerosol boxes. I've actually got, if I share my screen, can I do that?
Yeah, of course, yeah. I can stop sharing mine.
If I go to...
It's just at the bottom.
Okay. So we are looking at, can you see that?
Not just yet.
The visors. So an aerosol box is a clear box which would sit over the patient's head during the intubation procedure. And the idea is that it would collect any viral loads, so any substances from the patient's mouth during the procedure to prevent it being passed on to the clinicians that are doing the procedure. And then also the visor manufacturing, so manufacturing visors locally within Cambridge.
Perfect. Thank you. Did you have anything to add, Charles? Or
Nothing to add at the moment, no.
Perfect. All right. Well, thank you both very much for your time today. And as I said earlier, this webinar will be available on YouTube by the end of the week. So just keep your eyes open for that. Thank you very much. Thank you. Bye.
All right.